Hello, everyone. This is the lecture for section 3.3, power functions and polynomial functions. So we're getting into the rhythm of, we're about to start graphing some polynomial functions, okay? And learning a couple of the things that, like, as we've seen in the previous sections, sort of if you see something in the function, right? You see something in the written out version of the function, you can expect something to happen on the graph. Okay, we're leading up to that with polynomial functions. Okay, the first thing we got to start off with is just power functions first. We have to delineate those and get a feel for those, and then we'll move on to the more general polynomial functions and use the stuff from power functions in polynomial functions so that we can see what the graph is going to look like. Okay, and we're going to be able to do this without any graphing calculator at all. Okay, so the first thing that I want to define is this idea of a power function, okay? And a power function looks something like this. Some k times p to the k can be any number, and p can be any number, okay? The k up front is known as the coefficient. It's just the number that lives up front. That's it, nothing special, okay? So for some examples of some power functions, right? Yeah, for some examples of some power functions, right? These right here, all of these are completely legit. Now, these don't look like it, right? The ones on the right-hand side, they don't look like it, but I can rewrite these as this. X to the -1 is that one, okay? The next one is x to the -2. We'll learn some more of these when we get to exponents, okay? The square root, hopefully you guys remember, that's x to the 1/2. And then this one is x to the 1/3. Some of you may not have seen these at the end yet. Okay, that's fine. We'll get to those once we get to exponents. Okay, but for now, I want to concentrate with the power functions where this p that's up here, right? The p is going to be bigger than 0. Okay, we will mess with these. We will eventually mess with these, but not yet. Okay, so first thing I want to show you guys is the end behavior of power functions. Okay, and what I mean by end behavior is as I go towards positive and negative infinity, as my ends on the x-axis go toward positive and negative infinity. So basically, if I look at the graphs down below, right, what the heck is my graph doing way out here? And what the heck is my graph doing way out there? Same thing for this one, way out here, right, and way out there. Okay? That's what I mean by end behavior. Okay? So now, how do we express end behavior? Okay? So that's where I need to show you guys the graphs that are right there at the bottom right here. Okay? Notice, okay, all of these graphs, so this is the x² graph. Okay, this is x to the 4th, x to the 6th. Those are 3 different graphs where the power is even. Okay, and notice the shape that it takes. It always takes a U shape. Okay, so now to denote this, to write this down on pen and paper, right? How do we denote it? Okay, and this is sort of like the beginnings of how we are going to write stuff once you get to calculus. Okay, so let me show you guys what I write. So as x approaches negative infinity, right? This is saying this little thing right here is saying that my x values are going toward negative infinity. So that means it is becoming very, very large in the negative direction. Okay, so what we say here is this: as my x approach negative infinity, right, my y values approach infinity. So basically saying this, that as my x values go that way, right, my y values just shoot upward. And that's exactly what the graph is doing, all of these, right, as we approach, as we get bigger and bigger negative numbers on the x-axis. Okay? Okay, so this is what we say to describe this end behavior for even power functions. Okay, Likewise, okay, over here, we would say as x approaches positive infinity, let me move that up a little bit. As x approaches positive infinity, my y's approach infinity. And if you guys look, right, as we go that way on the x-axis, my y values just shoot upwards. My y values just shoot upwards. Okay, so this right here is how we describe the end behavior on that side for even functions. Okay. Okay, now let's take a look at the odd functions. So the ones on the right-hand side of the screen. So odd power functions, look at the shape it takes. It takes this squiggle-looking thing. Okay, and that is for anything that's odd. Okay, so if you guys take a look here, this is x to the 7th, this is x to the 3rd, this is x to the 5th. All of these have this kind of shape to them, this little squiggle. Okay, now to write the end behavior for these, right, we use the same sort of logic, right? So as x approaches negative infinity, right? So as we go this way on the x-axis, what's happening to my graph? It is taking a nosedive. So they're going downward, right? So we say here, as x approaches negative infinity, my y values approach negative infinity as well. Okay? Likewise, let's go that way on the x-axis, right? So as x approaches positive infinity, my y's approach infinity. And hopefully you guys see this, right? Not exactly what I wanted to do. That as I go this way, on my x, my y values shoot upward. They shoot upward that way, okay? This is how we write down the end behaviors for our power functions, okay? And this is going to be pretty important, as you guys are going to see in a second, okay? So, as an example, right, let me take this example right here. Let's say I wanted to describe the end behavior of this right here, negative x to the 9th, okay? So hopefully you guys see, right? I'm going to sort of draw a graph here. Very, very crude graph. Very, very no detail, right? It's x to the 9th. So that's an odd power. So that means our graph should do something like this. It should start from down here, go up that way, right? Now, there is that negative that's right there. That means, just like it did before, right? That our graph is going to be flipped. So my graph does this. This is a rough sketch. Let me do it again. This is a rough sketch of negative x to the 9th. It doesn't have to be exact for now. Okay? Okay, so now that we have a picture sort of in our mind or on a piece of paper down to refer to, right? Let's say we wanted to describe the end behavior. So we have to do the x goes to infinity and the x goes to negative infinity, okay? So if we see, right, for the first one, as x goes to positive infinity, right, as we go this way on our graph, our y values start to drop, right? So then we can say that our y values tend to negative infinity. And then if we do the other side, as x goes to negative infinity, that way, right, my y values shoot upward. Y tends to, let me write those arrows correctly. Those are arrows, there we go, tend to positive infinity. And we are done. So we are describing here, right? Hopefully you guys see that. We are describing our end behaviors. What happens to our graphs as we go really far on the x-axis in either direction. Okay? They don't have to be the same. They can be different. That's all right. Okay. I've got a couple quick checks here for you guys to try. These should be quick. We might not take maybe 2 or 3 minutes on it. Yeah, you can try these out at home. Okay? All right. Now we get into the good stuff. Identifying polynomials. Okay. So now we're getting into the bigger, more general section of what a polynomial function actually looks like. A polynomial function looks like this right here. Okay, n has to be non-negative, so it's just some positive number. Okay, and you guys see these ace of n's. So this one, and then there's an a2, a1, a0. Those are all what we call coefficients. Okay, and they can be any number we want. It can be any number they want. Okay, they can be 0, they can be negative, they can be positive. Okay, and each collection of these, so this right here, this, basically each one of these, right? Some ai x to the I is a term of a polynomial function. We call it, the terms of a polynomial. Okay, all right. Some more key terminology that we need to cover. Okay, in particular, let me undo the highlighting really quick. Let me put back the highlighting. In particular, what we're going to be looking at is this term up front. Okay, some important things there. Okay, that ace of n, the coefficient for that very, very first, the biggest term, okay, we call that the leading coefficient. Look at me go. I, E, and T. The leading coefficient, okay? The highest power that we see, in this case, the highest power we're assuming is the n, right? We call that the degree of the polynomial. So if that is a 2, right? If the highest power you see is a 2, that is a second degree polynomial. If the highest power you see is a 5, that is a fifth degree polynomial. If the highest power you see is a 10, that is a 10th degree polynomial, okay? And what that thing does, we'll study this a little more in a second, okay? We are going to touch on it today in this section, okay? It denotes the number of roots. And if you guys remember what a root is, the root is the zeros, right? Or the x-intercepts, okay? So the degree gives you the number of x-intercepts for a polynomial, okay? And then the last thing is that whole term that I have circled with my space pen, okay, that is also called the leading term. That is called the leading term, okay? Okay, some things that that I need to sort of give you guys, okay? Let me define this first, a turning point of a graph, okay? It's exactly what you think. A turning point is when the graph changes direction, either from increasing to decreasing or decreasing to increasing. Just basically, if a graph is got a turn in it, then it's going to end up going the opposite direction. That's it. Okay. Now, what's important for this is the theorem that follows. Okay. Suppose you have a polynomial of degree n. Okay. Then that means you have at most n x-intercepts and at most n minus 1 turning points. Okay, so what does that mean? So really quick, right? Suppose you had a fifth degree polynomial, so a polynomial of degree 5. Okay, the most number of x-intercepts you're going to have are 5, and the most number of turning points are 4. That's what this thing is saying, and you can do that with every number. Okay, and it's at most. It doesn't have to have that amount exactly. We're going to touch on that a little bit in this section and a little bit in the next section. Okay, now, what I do want to show you guys is this, that it turns out that this leading term, this ANXN that's up front right there, okay, that term describes the behavior of any polynomial function. So it describes the behavior of the graph itself. Okay, so what does that mean? That means I just need to look at this thing, and it'll tell me what the shape of my polynomial is going to be. Okay, got it? Okay, so what I want to do is, okay, so hopefully this works out right. I'm going to zoom in a little bit because I've got a table down below. There we go. Yeah, okay. So what I want to do in this example is show you guys how, what I mean by the theorem that's above, right? That the leading term describes everything. Got it? Okay, so let's start off with this function right here. This is my function, okay? The leading term, 5x to the fourth, okay? From the theorem that's given up above, right, we have roots and turning points. Turning points, turning points, turning points. Got it? Okay. According to this leading term, this is the biggest power we see, right? According to the theorem from above, there should be at most 4 roots. And I'm going to put at most. Okay, at most 4 roots. And the number of turning points should be 3, at most. Got it? All right. Now, end behavior. This is where we get to draw this thing. So that thing right there. We're going to end up trying to give a nice little, how did I say this? A nice little rough sketch. Okay, so we're going to put down an XY. Okay, this right here is an even power. So we know that our graph is going to do something like this. It doesn't have to do exactly this, but we know it's grossly going to do this. That is going to drop, right? Squiggle, squiggle, do some stuff down here, and then it goes back upward, right? So it's going to have like this sort of general U shape. Got it? Okay. This in and of itself gives us enough to describe the end behavior. So x goes to positive infinity. Well, let me do it the other way around. X goes to negative infinity, and the other side we're going to do x goes to positive infinity. Okay? As we see, right, as I go this way on my x-axis, my y values shoot up. So in this case, y goes to positive infinity. And likewise on the other side, y goes to positive infinity as well. There it is. We have a general idea of what our graph is going to look like. Okay? That because of this leading term, because of that leading term, that right there, we know that there's going to be at most 4 roots, at most 3 turning points. The graph is going to look like this, and our end behaviors are going to be like that. Okay? Okay, here's the fun part. I'm going to scroll over. There we go. That is the actual graph of this function. We are done. We have at least a nice general idea of what our graph is going to look like. Okay? Okay, let's try another one. Let me scroll so that we get, there we go. Okay, again, 2 to the 6th is our leading term. So we really care about negative 2x to the 6th. Okay? Turning points and roots. So roots and turning points. So the number of roots we should have is at most, right? Or the number of x-intercepts we should have at most 6. And turning points we should have at most 5. Okay, here's the fun stuff. Okay, here's our x and our y. If we graph this, if we try to draw a nice crude graph of what this thing is going to look like, this is an even power. So we know that our graph is going to do, and first of all, it's an even power. and there's a negative up front. So a positive one, a positive x to the 6 would do something like this. It's going to go, maybe do some squiggles, and then go straight back up, right? But we don't have this. We have the negative of it, right? So all of those go away. We have something like this now. We have something that is U-shaped. So a general, hopefully you guys see that. It's a general U shape, face down. Okay? Okay. X goes to negative infinity. X goes to positive infinity. Okay? You guys see that as I go this way, my y values are dropping. So my y tends to negative infinity. And likewise for the other end, y goes to negative infinity. Okay, you guys ready for this? You ready for it? You ready for it? Here we go. There's the actual graph. There's the actual graph. Okay, we have everything correct, right? The only thing that's kind of funky is this one. We don't see the 6 roots and the 5 turning points, right? But that's what the theorem says. It has at most. We're getting closer to it. That's going to be the way that we're going to explain this is going to happen in the next couple sections, okay? But for now, right, this is giving us a pretty good idea of what a graph, a polynomial is going to look like. It's given us a crude explanation and a crude, how do I say this, picture, right, of what one of these is going to look like, okay? Let's do one more. Okay, this one. Okay, hopefully you guys see the leading term, 3x to the 5th. So at most, hopefully you guys are getting used to this, right? Roots, 5. Turning points, 4. Okay. 3x to the 5th, the entire graph of that, it's an odd function, so it's going to look like this. It's going to have something that goes up like this, a bunch of maybe squiggles right here, and then shoots back upward. It has that S shape. It has this whoosh for an odd graph, right? Okay? Okay. X goes to negative infinity. X goes to positive infinity. You guys take a look, right? Just like I did before, as I go this way, my y values are dropping. So this one goes to negative infinity. This one would go to positive infinity. Okay, and let's do this again. I'm going to scroll over. There's our graph. Like I said, it's crude, but it gives us an idea. It gives us an idea of what we're looking at. Okay, one more just to nail it down. Okay, last one, this one. Okay, leading coefficient, or leading term, sorry, negative 6x to the 3rd. Okay, at most. Roots, 3, and turning points, 2. Got it? Okay, graph. We need to graph this one. We need to graph this. Okay, x to the 3rd is a squiggle. It's one of these. Now, it's one of these if it were positive, right? This has a negative in front of it. So we need to flip it. Got it? So our graph is actually going to do this. It's going to whoosh, whoosh, down that way. Gives us everything we need. As x approaches negative infinity, x approaches positive infinity. I like to write them out before I do anything with them. Okay. Okay. As we go toward negative, so as we go this way, you guys hopefully see my y values are shooting upward. That's what my graph is doing. So that means my y values tend to positive infinity. And for the other way, as x goes to positive infinity, so bigger positive numbers, right, they are taking a nosedive. So y goes to negative infinity. We are done. And again, just for kicks and giggles, let's scroll over. There's our graph. It is crude. It does do a whole lot more than we expected it to do. It has a massive squiggle in the middle, right? But, right, as a crude example, it's got everything we needed. Okay? All right. So now, we're getting into the good stuff. I keep saying that, right? Uh-oh, uh-oh. I keep saying that, and then the good stuff passes, and I don't mention it to you guys. Okay, so what we're getting good at, or we're about to get good at, is this right here. So you guys are going to start seeing two versions of polynomials, okay? One version is what we call the factored form, which is what we have here, okay? And the other one is going to be the expanded form, okay? So what I want to show you guys is how valuable this factored form is, right? And why we had to cover it at the beginning, very beginning of class. Turns out the factoring that you guys did at the very beginning with the diamond method, that helped us do so much more when we get to this section, okay? So first thing I want to do for this question, right, is we're going to use the factored form to find the x-intercepts. Okay, so if you guys remember the x-intercepts, right, this is where we set the y equal to 0, solve for x. Okay, so that means, okay, that we have to set this equal to 0. So now, let me repeat something from maybe like the first week of class, maybe second week. Okay, suppose you had an a times a b and it is equal to 0. Okay. Suppose you had two numbers, you're multiplying them together, and it's equal to 0. What can you tell me about one of the numbers? Well, you recall, either A is equal to 0 or B is equal to 0, right? Those are the two conditions that we have. This is, I believe, I want to say, from section 1.1 or 1.2, I believe, okay? Okay. We have the same scenario right here. We have a product of stuff. We have a product of stuff. So it's x times x plus 1 times x plus 1 is equal to 0. Okay? That means one of these three things has got to be equal to 0. So we make all three of them equal to 0. You guys remember that? Hopefully. So that means this is the case. Either x is equal to 0, x plus 1 is equal to 0, or the very last one, even though we already did it, is equal to 0. Okay? This one's already solved, but the other two, those require solving. And thankfully, it's the same thing, right? So minus 1, x equal minus 1, x equal minus 1. So my x-intercepts are going to be 0, 0, negative 1, 0, negative 1, 0. This right here, this one, these two happen twice. That's fine. No problem. Okay? But if you take a look at our theorem, right, that says that it has at most 3 zeros, right? Then it all fits. Now, what do I mean by the 3 zeros, right? Let's go ahead and expand this. So let's grab x plus 1, x plus 1, and expand it out. Okay? And that means I'm going to have to FOIL everything. Okay? So what I'm going to do is this. I'm going to grab these two. I'm going to FOIL those. So first, outer, inner, last. So I'm going to do the x stays outside. I'm not going to play around with that x yet, but I'm going to do the x times 1, the x plus 1 times x plus 1. So it's going to be x squared plus 2x plus 1. So if you do that stuff correctly, you get that. Okay? So now I have this x out front. I get to distribute this into all three. That produces x cubed plus 2x squared plus x. Both of these functions, this one and this one, are exactly the same thing. One of them is what we call the expanded form, okay, which is this one, and the other is called the factored form, okay? Hopefully you guys see why the factored form is really helpful. It automatically gives you the zeros. It automatically gives you the x-intercepts. Okay? All right, so now, what do I want to do? Okay, hopefully you guys see what's coming here, yeah? Same type of question. So I'm giving you a factored form, okay? Using the factored form, find the x-intercepts, and then using the distribution to find the expanded form, that'll give us a sense of what our graph is supposed to look like. Okay? So first of all, let's go ahead and do the x-intercepts, right? So that's the one where we set this equal to 0. So all three of these have got to be made equal to 0. So 2x plus 1 is equal to 0. X minus 3 is equal to 0. And x plus 1 has to equal 0. Minus 1, 2x is equal to minus 1. X is equal to minus 1/2. Okay? Next one. Plus 3, x is equal to 3. Minus 1, x is equal to minus 1. So, one x-intercept is going to be negative 1/2 comma 0. Another one's going to be 3 comma 0. And another one's going to be negative 1 comma 0. So, we know, so watch this, okay? We know our graph, and I'm going to do it in this orange, has to cross in 3 spots, okay? It's going to have to cross at negative 1/2 right here, okay? It's going to have to cross at 3, so 1, 2, 3 right here, and it's going to need to cross at negative 1 right here. Got it? Okay, now what I'm going to do is I'm going to grab this and expand it out in all its glory. Okay. In order to do this, I think I would just repeat this as many times as you can. Okay. Just keep a track of everything. That's the horrible part. That's the worst part. Okay. There's going to be a lot of stuff floating around. Okay. So just keep a track of it all. Okay. So what I'm going to do first is I'm going to rewrite it really quick. So 2x plus 1, x minus 3, x plus 1. I am going to distribute these two first. And I'm going to leave the 2x plus 1 separate. Okay? If you distribute this purple section right here, okay, you're going to get x squared, okay, plus x minus 3x minus 3. The 2x plus 1 just comes along for the ride. X squared minus 2x minus 3. Okay? Okay, here's the nasty bit. I'm going to grab this. Now I have to distribute this in. Okay, so it's going to be, I'm going to grab the first one, do it to all three, and then I'm going to grab the second one. I'm going to do another different color this time. I'm going to grab the plus 1 and go in. This is where people lose it. This is where people sort of, how do I say it? They lose the math. They lose themselves in the math. Okay, keep a track of everything. Okay, it's a lot of small itty bitty math. That's the problem. Okay, so let me go ahead and do it. So 2x times x squared, that's going to be 2x cubed. So I'm going to go from here to here. Okay, 2x times minus 2x, that's going to be minus 4x squared. Okay, 2x times negative 3, that's going to be minus 6x. We are done with the 2x. We move on to the plus 1 now. Okay, so it's going to be plus, and I'm going to do it right here. Okay, 1 times x squared, so it's going to be x squared. 1 times minus 2x, that's going to be minus 2x. And 1 times a minus 3, that's minus 3. So now, what I want to point out is this. You guys see how I wrote it? The cubes and the squares and the x's and the numbers, they are sort of grouped together, so I don't have to do much sort of hunting around for stuff, right? Okay, so now this becomes pretty easy to add. So this is going to be 2x cubed. We had a minus 4x and an x squared, right? I'm sorry, a minus 4x squared and a positive x squared. So that's going to be minus 3x squared. A minus 6x and a minus 2x, so it's going to be minus 8x. And then minus 3 that was lugging around at the end. So these two functions, these two right here, this one and this one, are exactly the same thing. Exactly the same thing. Okay, now, hopefully you guys see this. We get information from both. Okay, this one gives us the zeros, but it doesn't give us the shape of the graph, right? This one gives us the shape of the graph, but it doesn't give us the zeros. So both of them together give us a pretty good idea of what our graph is going to look like. This right here, so now that you guys look at this right here, right? This is a 2x to the cubed, right? 2x to the third. That's going to look like one of these. It's going to look like a squiggle. It's going to look like a whoosh, like that. Okay? We have an added amount of information here that it's got to cross these 3 points right here. Okay? So hopefully you guys see what's going on here, right? We need a squiggle that crosses these 3 points. It doesn't got to be perfect. It doesn't have to be perfect. So long as it goes, so something like that, whoosh. And if we go to Desmos, let's go to Desmos really quick. And I want to do a double. And I'm going to type in that very last one. 2x cubed minus 3x squared. Hopefully you guys are seeing this already. Minus 8x minus 3. Our graph, we said, was going to look something like this. Lo and behold, you guys see that? Look at that. We wanted it to cross at -1, -0.5, -1, -0.5, and +3. Done. Okay, so what I want you guys to notice is this, that both of these functions together give us a nice little representation of what our function is going to look like on the graph. Okay, and we're already seeing this, right? We don't even have to we don't even have to put this in Desmos. We automatically know that if we see these things, right, in our function, we know what they're going to do on the graph. Whew, that was a lot of good stuff. Okay, I've got some quick checks for you guys to do. We'll do these in class, okay? Give you guys some time to practice with them. After that, I think it is lecture questions, okay? If you have any questions about this, ask me during class. Besides that, happy studying.